So students, this is our lecture number 5 of design and analysis of algorithm, right? In this lecture, we will discuss what is recurrence relation and how to solve the recurrence relation with the help of given methods. Now, first of all, what is recurrence relation? Recurrence relation is an relation. Recurrence relation is an equation or relation which represents a sequence based on some rule. Now, 4 types are given below. Now, what are the 4 types? Number 1 is substitution method. Number 2 is iteration method. Number 3 is recursive tree method. And number 4 is master method. Now, let's discuss all the methods one by one. So, first of all, we will discuss substitution method. Substitution method, we can further categorize substitution method in 2 types: forward substitution and backward substitution. Let's discuss forward substitution first. In forward substitution, we uses the initial condition in initial term and generate the next term and keep on repeating the same process until we guess particular formula. We rarely use this method because we will have to guess the formula in this method, right? Let's take an example. T of n is equal to T of n minus 1 plus n, where T of 0 is equal to 0, which is obviously our initial condition, right? So let's solve this equation. Let n is equal to, let me take small n, let n is equal to 1, right? So T of 1 is equal to T of 0 from initial condition and plus 1 is the formula. So what we will get? 0 plus 1, we will get T of 1 is equal to 1. So we can call it equation number 1, right? Let n is equal to 2. Now T of 2 is equal to T of 1 plus 2 according to formula, right? So T of 2 is equal to, now we can put 1 instead of T of 1 from equation number 1. So what we will get? 1 plus 2. So T of 2 is equal to 3. Now we can call it equation number 2. Okay, let's take n equal to 3, right? So T of 3 equal to t of 2 plus 3. Now t of 3 is equal to, now I can put 3 instead of t of 2 from equation number 2. T of 2 is equal to 3, so I can replace t of 2 with 3. So 3 plus 3, it will become t of 3 is equal to 6. So I can call it equation number 3, right? So by observing, see, by observing equation number 1, t of 1 is equal to 1, t of 2 is equal to 3, and t of 3 is equal to 6. So what have we observed by looking at equation number 1, equation number 2, equation number 3? What have we observed? We actually came to know we are actually adding the sum of all natural numbers. So the sum of all natural numbers, what we are doing, we are actually summing, we are actually adding the natural numbers. So what should be the formula? Now we can guess the formula from equation number 1, 2 and 3. The formula to the sum of all natural numbers would be t of n is equal to n multiply n plus 1 upon 2, right? Let me write in this way for your convenience. Right? N multiply n upon 2. So when we multiply it, obviously we will get t of n is equal to n square upon 2. We will multiply it, n multiply by n square. So n square upon 2 plus n multiply by 1. Now n multiply by 1, n upon 2. Now t of n is, considering the big O notation, I have already explained you in lecture number 3, and then I repeated the same concept in lecture number 4. Whenever we have complexity in the form of equation, or whenever we have an equation, so we always consider the highest power. So considering the same rule, considering the big O notation, we only consider the highest power and ignore the rest. So considering that rule, I can write t of n is equal to O n square. O n square. Right? So here is the solution of substitution method, and specifically in substitution method, the forward substitution method, right? Let me revise all this for your convenience. Forward substitution is a method which uses the initial condition in initial term and generate the next term and keep on repeating the same process until we guess particular formula. So we rarely use this method because we will have to guess the formula in this method, right? Let's take an example. T of n is equal to T of n minus 1 plus n, right? Where the T of 0 is the initial condition, right? So what we have done at initial level, let n is equal to 1. So for initial condition, T of 1 is equal to T of 0 plus 1. So we call it 0 plus 1 equation number 1. Let n is equal to 2. So T of 2 is equal to T of 1 plus 2. So it will become T of 2 is equal to 3, equation number 2. Now do it for let n is equal to 3. Now T of 3 is equal to T2 plus 3. It will become 3 plus 3. We have replaced T of 2 with 3 considering equation number 2. Okay. So 3 plus 3, we call it equation number 3. You can even solve it for n equal to 4, n equal to 5, but there is no need to solve. By just observing equation number 1, 2 and 3, obviously everybody came to know okay, we are actually adding the natural numbers in each and every equation. So what have we observed by equation number 1, 2 and 3? We are actually adding the natural numbers in each and every step. So by looking at all the above equations, we guess a formula T of n is equal to n into n plus 1 upon 2, which is obviously a formula of adding the natural numbers, right? So when we multiply it, T of n is equal to n square upon 2 plus n upon 2, right? So considering the highest power and considering the big O notation rule, we only care about the highest power and ignore the rest. So T of n is equal to O n square. That's how we solve an equation using the forward substitution method. Got it? Now let's move on to backward substitution method. Now backward substitution method is a method in which backward values are substituted recursively. We generally use backward substitution method for problems like the factorial. The best example of a backward substitution method is a problem of a factorial, right? So let's take an example of backward substitution method. Let me take an example of a backward substitution method. Let's say I take an example T of T of n is equal to T of n minus 1 plus n, right, with an initial condition of T of 0 is equal to 0, right? Let me write terminator over here. Okay, where obviously t of 0 is 0 is an initial condition. Is an initial condition, right? So let's solve it. And we call it, so when we replace n with n minus 1, so t of n minus 1 is equal to t of n minus t of n minus 2 plus n minus 1. We call it equation number 2. What have we done? Starting from the first condition, we have started from the first condition, t of n is equal to t of n minus 1 plus n, which is our equation, and this is the initial condition. So we call it equation number 1. So because we are solving a backward substitution method, so we will start from one step back. So we replace n with n minus 1. So we replace n with n minus 1, right, in equation 1. So when we replace n with n minus 1, it will become t of n minus 1, and t of n minus 1, t of n minus 1 minus 1. So it will become t of n minus 2 plus n minus 1, right? It will become t of n minus 1 minus 1, right? So I can write it like t of n minus 2 plus, we replace n with n minus 1, so it will become t of n minus 2 plus n minus 1, and we call it equation number 2. Okay, everything is clear so far? Now let's move on. Now we will replace, now we will replace n with n minus 2. We will replace n with n minus 2. So what we will get? T of n minus 2 is equal to T of n minus 2 minus 1 plus n minus 2, considering this equation, right? N minus 2 minus 1 is the formula, plus n, we have replaced n with n minus 2. So when we further solve it, it will become t of n minus 2 is t of n minus 3 plus n minus 2, right? So we can call it equation number 3. can call it equation number 3. Okay, let's move on. Now suppose first we have solved it for n minus 1, then we have solved it for n minus 2, we can also solve it for n minus 3, but there is no need to further solve. Suppose I solve it for t of n minus k. Suppose I solve it for t of n minus k, so what will it become? T of n minus k plus n minus k plus 1 plus n minus k plus 2 plus the process will keep on going until the n. So if k is equal to n, then t of n is equal to t of 0 plus 1 plus 2 plus 3 plus 4 plus 5 till n. So t of n is equal to 0 plus 1 plus 2 plus 3 plus 4 plus 5 till n. What is this behavior? Obviously we are adding the natural numbers, right? So we can call it the sum of natural numbers, right? So it's a sum of natural numbers. Okay, so what is the formula of sum of natural numbers? We have already discussed in forward substitution method. So the formula for sum of all natural numbers is n into n plus 1 upon 2. N into n plus 1 upon 2. This is the formula, right? So when we further solve it, t of n is equal to n square n square upon 2 plus n upon 2. So considering the same big O rule, we only care about the highest power and ignore the rest. So t of n is equal to okay students, so here we can solve it by using backward substitution method. Okay, so students, we have just discussed substitution method, in which we had discussed forward substitution method and backward substitution method. Let's discuss another method for recursive relation, which is a recursive tree method, right? Now I have written a small pseudocode. I'll go check. I am passing an argument of type integer. If n is greater than 0, so this code will execute, right? If n is greater than 0, this code will execute and check will be returned by n minus 1, right? So if n is greater than 0, this code will execute and it will reduce n minus 1 each and every time it will call itself. Okay, so if I write the time complexity of the above code, the time complexity of this is Tn, right? The time complexity of this would be 1. The loop will run n times and plus 1 is for one extra time when the loop actually returns or it will reaches the approximate value. So n loop will run n times and plus 1 is one extra time when it crosses the limit, right? N is the time complexity of this statement. As you can see, the arrow indicates that, and check n minus 1 each time it will return n minus 1. So we can write the time complexity of this t n minus 1, right? So what should be the time complexity of the above algorithm or pseudocode? Tn would be the sum of, you can see the bracket, Tn would be the sum of 1 plus n plus 1 plus n plus Tn minus 1, right? So by adding we get, you can see that clearly, Tn is equal to Tn minus 1 plus 1 plus 1 2 n 2n plus 1 plus 1 2. So by adding this we will get Tn minus 1 plus 2n plus 2, right? So Tn is equal to Tn minus 1. We have written Tn minus 1 as it is. And what about the 2n plus 2? What about the 2n plus 2? Now, considering the big O notation, we only consider about the higher power. So I can write n instead of 2n plus 2. So the final recurrence relation would be Tn is equal to Tn minus 1 plus 1. This would be our final recurrence relation, right? From the above pseudocode, right? Let me explain once again. Here is an algorithm, algo check, which is passing an argument of integer type. So let me say that it will take Tn time. If n is greater than 0, it will take 1 time. The time complexity would be 1. For I is equal to 0, I less than n, I plus plus, it will, the time complexity would be n because the loop will run n number of times and plus 1 extra when it basically crosses the limit and the loop will terminate. 1 extra time it will take, okay? C out, it will print n, so I will take n, and every time it will return n minus 1. So I have written Tn minus 1. By adding this, I will get Tn is equal to Tn minus 1 plus 2n plus 2. So I have written Tn minus 1 as it is, and I have written, considering the big O notation, I will consider the highest power, so I will write n instead of 2n plus 2. Got it? Let's move on. So I have retrieved a recurrence relation. Here I have retrieved a recurrence relation. Tn is equal to Tn minus 1 plus 1. Tn is equal to Tn minus 1 plus 1. I have retrieved a recurrence relation. Got it? So Tn is equal to Tn minus 1 plus n when n is greater than 0, and when n is equal to 0, when n is equal to 0, it will do nothing. So I can write here constant, or I can write here, I can write here, wait a minute, I can write here constant, or I can write here 1. 1 also represent constant, right? So here I have retrieved a recurrence relation. If n is greater than 0, this relation will, this equation will execute, and if n is equal to 0, so 1, it will produce a constant and it will produce 1. Okay. So how to solve this in a recursive tree method? So let's solve recurrence tree of the above recurrence relation. The recurrence relation we have retrieved with the above algorithm, and now we are going to solve this recurrence relation with the help of a recurrence tree method. Got it? Let's move on. So here is the Tn basically which we are solving. Here is the n, Tn minus 1, right? Now every time it will break the list, every time it will be n minus 1. Each time the algorithm calls itself, it will be n minus 1 and n minus 2. Each time the algorithm calls, it will be n minus 1 and n minus 2, right? Just like that. If it calls another time, it will be n minus 2, n minus 3, right? And how long this process will go on and on? How long? Until or unless it reaches t of 1. How long this process will go on? Until it reaches t of 1, right? And t of 1 means obviously t1, and it will be t0, right? So if I write the time complexity of the above tree, the time complexity of the above tree would be t of n will take n time, t of n minus 1 will take n minus 1 time, t of n minus 2 will take n minus 2 time, t of n minus 3 will take n minus 3 time, t of 1 obviously will take 1, and t of 0 obviously will take 0. So if I ask you to write the complexity of the above tree, so obviously you will have to add the above complexity. So what will become if we will add 0 plus 1 plus n minus 1 plus n? So obviously it will become 0 plus 1 plus 2 plus n minus 1 plus n, n minus 1, n minus 2, n minus 3 plus n. So obviously what we are doing, we are just adding the natural numbers. And what should be the formula to add natural numbers? Here is the formula. Here is the formula to add the natural numbers. So when it will be multiply n square plus n upon 2 it will become n square upon 2 plus n upon 2, right? And considering the big O notation, we will consider the higher power, so it will be Tn is equal to On square, right? So here by this method you can solve the recurrence relation with recursive tree method, right? Again I am explaining you. Okay, I am again explaining you the recursive tree method. This equation we have retrieved from the above algorithm. If n is greater than 0, so this recurrence relation for n is greater than 0, we have got Tn minus 1 plus 1, right? And if n is equal to 0, n is equal to 0 means any constant will be produced. We can represent it with c, or I can call it 1. Okay, if n is equal to 0, it means the constant will be produced, nothing will happen, so we can call it constant or 1. So let's solve this recurrence relation tree, right? Now Tn minus 1 plus 1, here is the Tn minus 1 plus 1, right? Now again it will call itself. When it will call itself, so it will become n into n minus 1. Again it will call itself, so it will become n minus 1 and n minus 2, right? When again it will call itself, it will become n minus 2 and n minus 3. And how long this process will go on? How long this process will go on? Until this Tn, until this Tn will reduce every time till it reaches 0, right? This n will reduce every time till it reaches 0. It will call itself each and every time until it reaches 0. Got it? So if this Tn will keep on calling itself until or unless it will reach 0. So if it further call itself, it will become T of 1, and when it T of 1 will call itself, it will become T of 1 and T of 0, right? So when we add the complexity, so obviously it will take n time, it will take n minus 1 time, it will take n minus 2 time, it will take n minus 3 time, it will take constant 1, and it will take 0. When I add up, so by adding, it will become 0 plus 1 plus 2 plus n minus 1 plus n minus 2 plus n minus 3 plus n eventually at the end plus n. And what is happening over there? We are actually adding all the natural numbers. So eventually we will get this formula of adding the natural numbers. So when we multiply it, n square upon 2 plus n upon 2, so Tn is equal to n square upon 2 plus n upon 2. Considering the big O notation, we will get Tn equal to On square, right? So as far as theory paper is concerned, you will have to solve the whole equation whenever you will be asked to solve the recurrence relation with the help of substitution method or recursive tree method or master theorem method. Well, as far as theory is concerned, you will have to solve all the steps. But while programming, while doing practical implementations, you don't have to solve the whole steps. When you will be in a position, when you will be in a practice, when you do more and more practice, you will be in such a position where you can just retrieve the answer by just looking at the recurrence relation, right? So as far as theory is concerned, you will have to write the whole steps, you will have to write each and every steps, but for practical purpose you don't have to write the whole steps, but do more and more examples of recurrence, of Fibonacci series, of Tower of Hanoi, of factorial, etc., etc. So whenever you will get expertise, then you will be able to solve the recurrence relation by just looking at it. Okay. So at the end, I conclude my lecture. In next lecture, I will be explaining the master theorem method.